Okay, so welcome everyone to this webinar by Mira Mezini. Before starting with her webinar, let me just spend a few words to introduce Informatics Europe, which is an association for informatic research and education in Europe. So Informatics Europe represents public and private research community and has the objective to create a strong common voice to shape the quality of research and education. So the focus is in fact in education research, but also knowledge transfer and the analysis of social impact of informatics. So we want also to pay attention to how we can help the society in this period in which informatics is becoming more and more relevant in this area. We have 160 members from 34 countries, which are the ones that you see here. So almost all countries in Europe, in broad Europe, are represented. Our goals are to foster quality of research and education, to promote knowledge transfer and collaboration between academia and industry, to engage with society, and to promote high quality standards and best practices in research education, and also in knowledge transfer. So here we have an overview of the activities that we perform. So as I said, we are active in education, research, etc. And here you see the working group, the permanent working groups that we have created and that are led by volunteers in the association. Then whenever this is needed, whenever there is a specific problem that we want to address, we set ad hoc task forces to focus on specific aspects. Of course, we really welcome any proposal for new initiatives that each member wants to do, and we are happy to contribute to the development of any initiative in the areas in which we are focused. So research, education, knowledge transfer. In terms of events, we have an annual conference, and we invite you to participate in this annual conference. This is ECSS. So the next one will be in October 24, from October 24 to October 26 in Hamburg. Hopefully it will be in presence, and we do hope to see you there. We have a webinar, actually a couple of webinar series for the moment, and one of them is this series that is focusing on scientific webinars. We also have what we call an academic leadership development course, which is given out online, at least for the moment. And this is quite useful for young people, but also not necessarily very young, who need to take some leadership role and need to get some training in this area. So let's now focus on the webinar. I think Professor Mezini doesn't need to have a specific introduction. She comes from University of Darmstadt in Germany, and the title of her talk is Programming Distributed Decentralized Applications. So please, Mira, I am stopping sharing my screen. So wait a second, I don't know how to stop. Okay, there is a button. Okay. Maybe you are muted. Okay.
Okay, so now everything should be okay. You see my screen, the presentation, not the presenter notes, right? So everything's fine. Okay, so thank you, Elisabetta. Thank you for inviting me to give this talk in the series of Informatics Europe's webinars. The title of my talk, I mean, yeah, you introduced me. I am professor at the Technical University of Darmstadt in Germany and lead there the software technology group, but I'm also involved with a couple of other centers at TU Darmstadt or in Darmstadt. And you see the logos at the bottom of the slide. Emergent City is about emergent resiliency of smart cities. Hessian AI, as the name says, is about artificial intelligence, and Athena is the Center for Cybersecurity. With this, let me start with the talk. And the title of the talk is a little bit broad, so I will start by explaining a little bit what I mean by data-driven and decentralized applications. Well, I guess everybody knows when we talk about data-driven applications, what I mean. In this class, one subclass of such applications are our social apps, like instant messengers or multiplayer games. But in the same class, there are like collaborative workflows, like Google Docs and Figma and Trello, but also environmental condition monitoring or real-world enterprise software. What these applications have in common is that basically they are driven by data, and via them, data drives the change in real world and real time. And now to explain a little bit what I mean by real time, because it's not the traditional meaning of real time that we all know, let me show you a very quick demo of an example application in this class, basically a shared to-do application.
I don't know if there is an audio. We cannot hear the audio.
Okay, so then I will speak instead of the audio. Okay, so it's a to-do MVC case study. Basically, it reacts to user input, updates its state, and displays the updated state back to the user. We can change the state, and then we observe a time-changing behavior of the application. And while this is a very small example, I mean, realistic applications of this kind have or work according to the same principles. Now, they typically have not only one node or run on one node, but on several nodes on several devices. Assume I want to have this to-do list across my devices or collaborate with my colleagues. So I can connect between the devices, and then once the connection is established, the state of the devices is synchronized. And I can have pairwise connections across several devices, more than two, and the changes on one device are instantly or real-time propagated to all devices, made visible to all devices. Now, being in a distributed system, there can be crashes, like let's say the node B crashes, which is simulated by reloading the frame. You don't see much of a change because the state is restored after the crash, but changes are no longer synchronized. But I can work offline, and then once I connect again, the state gets automatically synchronized, and moreover, even when this device B gets back and is connected, its states also gets consistent with the rest, a property which is known as eventual consistency. Now, we do have this kind of applications today, but they follow or they're implemented following kind of a centralized architecture, data and computations are managed in centralized geo-replicated clouds, while our devices are basically, if you want, user interfaces. And this model stems from a time where data existed in the cloud. Think about Google search index or Amazon book information, and clients or devices were pretty poor in terms of resources that they had. Think about web clients without the possibility to execute code, or mobile phones before smartphones. I mean, this centralized architecture is, if you want, kind of mainframe computing 2.0, not quite. I mean, we have made a lot of advances, but still in principle, the idea remains. And the model is kind of doesn't fit very well with the reality of today's computing, where basically the new data centers are things like our very powerful smartphones, or we have these data centers on wheels, the modern cars, even not self-driving ones, but traditional ones, have very powerful chips, are basically have several computers in them that are connected to each other. And then think about these data centers on wheels being connected to each other across cars, which basically results in a massively distributed computing infrastructure. But not only this, like we have drones that are basically small data centers with wings, and even kind of a street lamp is nowadays, or can be nowadays, a computer with several components in it for sensing and processing data and acting to the world. And then basically our forests are getting interconnected, I mean, with a lot of sensor in them, and agriculture 4.0. Actually, we have a lot of devices and small data centers on the field. And yet these very powerful devices still, in most of the cases, serve basically as user interfaces or as sensors and actuators. Again, data management and processing happens on centralized clouds, which kind of wrap around geo-replicated data centers. Now, this centralization is not good for several reasons, or we need kind of decentralization. Well, there are functional reasons, like it's not good for latency or reliability, offline availability, or even it might be a no-go when we talk about in-the-field computing, where there is, if at all, intermittent connectivity. But there are other reasons, like ecological reasons. We store a lot of data, even if it's not used as dark and raw data, which has its own CO2 footprint. We don't kind of reuse existing infrastructures, like, as I said, our very powerful smartphones and mobile devices. And there are socio-economic reasons, like the control over data is not with the data producer, so data privacy is an issue. There are no possibilities, for example, that people can have some digital income out of their data or out of their computing infrastructures. And there are economic costs associated with storing and evaluating data and complying with data insights and the like. So there is this move towards more decentralization, towards moving computations from the cloud down to the edge where data is produced. And some fellow researchers talk about local first software, local first applications, where data is generated on local devices, want to be processed in local devices, and may be shared on demand or with remote devices when this is necessary. So this is what I mean by decentralized applications. And so far in this very first part of the talk, I basically have explained what I mean by data-driven applications. I explained that the dominating programming paradigm for those applications is a centralized one, relying on centralized clouds. that this model is broken for several reasons that call for decentralization. And now in the second part of the talk, I will argue that existing programming foundations for this kind of local first or decentralized data-driven applications are not well suited, especially, I mean, the picture is very big for a talk, so I specifically will focus on foundations for managing data and their flows. Now, our abstract foundational model of computing is pretty simple. In this model, memory is ordered in, let's say, in an array, which is accessed by programs by the CPU in a synchronous way. But this is way back. We lost this simplicity again a while ago, when, for reasons of improving availability, we basically replicated computations across different computers. When we say the computing went big or bigger. So this is where already where ARPANET or the internet was born, basically the grandfather of the geo-replicated data centers in the cloud today. And this move was a good one for availability and efficiency, but we lost universality in the sense that computations that were possible before were not possible anymore without consensus and coordination. And the problem is basically the same when we go to the world of multi-cores, to the infinitely small rather than infinitely big. But I will focus on the first part only. Now we lost universality, so we needed coordination, and the traditional way for re-establishing order on state basically were coordination protocols with their underlying theories, which very abstractly were great because they ensured application correctness by design. To make it a bit more concrete, one of those protocols were database transactions. The theory underlying them is serializability, and the engineering methods made out of this theory basically ensure transparent illusion of order or simplicity. But we know these coordination protocols, great as they are for application correctness, were challenged in the sense of being expensive or even sometimes unaffordable, because we know old CAP theorem saying that we cannot have all three of those, consistency, availability, and partition tolerance at the same time. We have to make the choice. And I mentioned that for local first applications, availability is needed, is must, and partition tolerance is a given. So we have to do something about consistency, but not go on the way where all this NoSQL solutions went, basically using design patterns, if you want, commutative reverse methods, compensation, which were great for enabling scalable infrastructures, but at the same time at the cost of losing or making it tricky to ensure application correctness, which maybe was okay for as long as the same teams at Google and Amazon developed the infrastructure and the applications at the same time. But when we talk about moving computations and democratizing, so to say, local first applications, we have to think about ordinary developers, and we want to ensure correctness by design, but at the same time in an affordable way. And one important step in this direction was this new theory of eventual consistency or replicated data types. One particular kind of those replicated data types are the so-called conflict-free replicated data types. The theory behind them is lattices. So conflict-free replicated data types are data types whose state can be represented, whose state domain can be represented as a join semi-lattice. Basically, there is a join, a merge operation of the state, which has certain mathematical properties. The merge is associative, commutative, idempotent. I mean, the distributed property is added by by Joe Heller's team, just to allude to the ACID property. So the new ACID, a property of eventual consistent systems. So a very simple example of CRDTs is a set with the union operator as the merge. But the good news is that a lot of data types actually have representations that can be implemented as CRDTs. And there is more that has happened in this space. These are a few papers, but there are many more, like, for example, the mergeable replicated data types. The work kind of proposes an approach to automatically, so to say, derive merge operators for any kind of data type, given that there is a relational specification of the data type which can automatically can be used to derive the merge operator automatically. So far, so good. So basically, we can conclude that we have refined and improved a lot the central geo-replicated clouds. So we have managed somehow to cope with this broken state in that setting. But in today's computing, these geo-replicated clouds are basically only one element in the big picture, the top here. And the solutions that were developed for this particular setting are not directly applicable to local first computations. So why? Well, these computations in the geo-replicated clouds operate in a rather controlled way, one could say. So data centers are connected with, I say, relatively stable connections. There is a reasonably manageable cyber attack surface. These clouds are managed by distributed systems engineers in cloud and platform companies. And these characteristics do not hold for the edge data centers, right? Distribution on the edge is not a technical means to enable availability and scalability, and concurrence is not a matter of speeding up computations. Both of them are kind of inherent properties of the world, of people, devices, data sources being inherently distributed and acting and reacting inherently asynchronously in time and space. So in this setting, nodes come and go, connections are much reliable, and the attack surface is, of course, huge. Moreover, the solutions for data management in the centralized world kind of were tailored toward processing stationary data. So, and they do not directly cover the need for end-to-end management of entire data flows in real time. I explained what I mean by real time, right? So instantly, everything that depends on something gets automatically updated when this something changes. So in this new setting on the edge, it's not enough that the replicas of some piece of data get synchronized. It's also the insights that are inferred or derived from this data and that live on some device up to the GUI views. Everything needs to get synchronized, as I said, in real time. And this kind of end-to-end synchronization of entire data flows in real time brings its own disorder into the picture. Again, our abstract model of computing kind of is a synchronous model. Instructions are ordered in a list and executed in the sequential order in which they appear in that list in the program. So our model is pretty much control flow driven. The order of the computations in our data driven applications is not determined by the order of instructions, but rather determined by arrival of data and events from the external world. And in principle, you could say, okay, this is not a new problem. We have had interrupts all the way, but now they are not anymore the exception. The interrupts are the norm, so to say. And there is this mismatch between data flows and control flows. And basically our approach to reconcile this mismatch has been callbacks. So attaching callbacks to events or to changes to data to react to those changes. And this approach has been characterized as the callback hell to indicate that it led to very complex, hard to maintain, hard to reason about designs and hard to keep the state consistency of the application. The problem here is that the application developers are playing, to my point of view, compiler. So they have to set up callbacks and manage their life cycle as part of the application logic. And again, they are also responsible for ensuring consistency of application state, again, as part of the application, which leads to very, very complex designs, even for such a very simple logic where I just want to encode how the current hour, day, and week changes whenever some input sensor, a tick occurs. Even if the functionality, the logic is as simple as it is written here, if I was able to just declare the logic, the corresponding encoding in a Scala-like language, which even has events and the possibility to attach callbacks to the events, ends up being that complex, which makes it hard. So we end up with a lot of boilerplate code, and more importantly, we end up with the logic of the same, I mean, a coherent piece of logic split across different callbacks, which interact with each other, collaborate with each other via broadly scoped shared variables, which basically makes it hard to ensure consistency and reason about. So to sum up this second part of the talk, in summary, we can say that with computing getting distributed, disorder and broken state became the norm. Consensus became necessary for universality, but is challenging. And the open and dynamic real-time nature of today's decentralized data-driven applications just amplify the problems. And again, with decentralization, we cannot rely on skilled teams at cloud companies to ensure application correctness. So basically, we need to bring the illusions of simplicity from the centralized setting on the edge and on device, and of course, do so in an affordable way in terms of performance. And I will argue basically that we need to make consistent data flows first principles of local first programming. I argue for programming language-based transparent illusions. So have programming languages support consistent data flows from the ground up, built in. And the reasoning for PL support-based approach is simple to my point of view. Languages give meaning to programs, and programs encode the application semantics and know best about the application semantics, which can be used by the language machinery to automate concerns. And in the rest of the talk, in the third and last part of my talk, I will briefly present you REScala, which provides declarative programming for data-driven local first applications. REScala is a language that we have been developing in my team in the last couple of years. You see some of the team members on the slide, and there is a lot more very talented bachelor and master level students, that a whole army of them that have contributed to REScala as it is today. As I mentioned, I will very briefly introduce it, and more information is available from the REScala webpage, I mean, including the GitHub repo, including tutorials and other documentations, and also quite some case studies. Anyway, so let me start by explaining how REScala supports managed data flows first. And to give you an intuition of what I mean by managed data flows, let me draw your attention to a well-known domain-specific programming model that features such managed data flows that also is very well known to everybody, I guess. And I'm talking about Excel sheet programming. When you program an Excel sheet, you define either simple values in a cell, or you define values that are declaratively composed by mathematical operations out of other values, out of other cells. And when you change a cell, anything that depends on it transitively is updated automatically and consistently without you defining any callback. And basically, you could say broadly that REScala turns this into a general purpose principle, this managed data flows. The reasoning is, I mean, if your applications are driven by data flows, if data flows are so central in the applications, then you shouldn't basically leave the responsibility of managing these data flows in a consistent way ever and ever again to the shoulders of the developers. We have the dry principle, don't repeat yourself. If this is a concern that goes across several applications, then make it a feature of the language. That's basically the reasoning behind the managed data flows in REScala. But what does it mean concretely? Basically, the core abstractions of the language are the so-called reactives, and there are two kinds of them, events and signals. You all know what events are probably, and signals may need a little bit of more explanation. Basically, they are first-class time-changing values in the language. Time-changing values mean I define values by composing other values, and whenever some value changes in the system, all other values and expressions that depend on this transitively get up to date. A simple way to explain is time-changing values or signals is by saying that they introduce a new evaluation regime. We have call by value and we have call by need, and now we have call by reaction. You don't call functions directly, they are called automatically whenever their parameters, their inputs change. Now, being first-class value in the language, signals can be arbitrarily composed into more complex. We use the term derived ones. And the language also offers some predefined combinators like fold and map and filter and zip. And the key point is that changes, arrival of new events or changes of source signals, simple signals, get automatically and consistently propagated to dependent computations. To go back to our running example, the reactive to-do list. This is how the program looked like. Ignore for the moment the orange arrows. They were meant to be animated and not on the slide at this point. And you don't need to understand or read the code. I will kind of guide you through the code. Basically, all you need to notice is that there are some values that we define, like remove all and create to do and create task and task list. And then some values are defined by combining previously defined values like, let's say, create to do and remove all and create task are all used in the definition of a task list. This is the orange arrows show this kind of relationships. And then task list is basically passed as a parameter to the display operation of the UI. So that's it, that's the program, and there is no callbacks in it, right? So every time, and nevertheless, every time task list changes, because let's say a new task is created or a new to-do is created, then the display will get automatically updated. Now, what makes this possible, these managed reactions or managed data flows, is behind the scenes the so-called dependency graph. So the REScala compiler kind of turns all these signal computations into nodes in a dependency graph. And it's the runtime that manages this dependency graph. Any change that comes from the outside world goes through the kind of propagation algorithm, which then starts re-evaluating all nodes in the graph that depend on that change. And every time a node is re-evaluated, then the user-defined signal computations are executed, eventually having effects on the external world again. The key thing to ensure what I call consistently propagations is the synchronous semantics of change propagations through the graph. What is meant is that any change is kind of starting with a consistent resting state of the overall graph. Any change, any update propagation moves the whole graph into a new consistent resting state in an instant, if you want. That means we don't see from the outside, there are no observable intermediate changes. And you see this, probably this is best illustrated by this change, which the orange one here, which affects the node in the middle via two paths. And nevertheless, we will see only one new value of that computation, even if the node is reached via two paths. This is achieved by kind of traversing the dependency graph in a topological order. So there is at most once execution semantics, which results in a glitch-free semantics of flows, meaning that we don't see intermediate values. Now that's all about the basics. We can conclude that with this managed data flows, we move from a world where we have programmatic tracking of data flows between computations in the application code to a world where we have automated management of data flows through computations. And this has several advantages. It makes the design simpler, and it makes it easier to comprehend the software. We have done small empirical studies, one of them showing the positive effect of this kind of programming style on software comprehension. But I don't have time to go into more details about this. What I want to emphasize is that this declarative style of programming enabled by managed data flows is important not only for making program comprehension easier, but also is key in enabling the runtime of the language to ensure consistent data flows. And let me start by talking about what we call serializable flows, or serializable concurrent flows. So I mentioned that flows in REScala are glitch-free, but then when you have flows that happen concurrently but share nodes in the dependency graph, then glitches can occur again. You can see non-deterministic behavior if you don't manage this disorder that comes through concurrency. And ideally, we want basically to, although the two flows, the green and the orange, execute concurrently, we want to make them appear as if they happened once after the other, moving the state of the whole graph from one consistent resting state to another consistent resting state, and so on. And basically, that's what we do with the serializable flows. We basically consider, if you want, each flow as if it was a transaction in a database sense, and then we make sure that these transactions are serialized. And with very strong, actually, properties, we prove that they execute with abort-free strict serializability, and especially this abort freedom is very hard to achieve even in traditional serializability models. But it gives us a lot of power in the sense that it's kind of a syntactically and semantically transparent illusion, meaning that there is no way I can distinguish between running the same REScala program without changing it on a single-threaded or multi-threaded environment. There is no change in syntax, and I cannot observe any change in behavior. And I put the affordable here down here in gray because I'm not going to talk about it, but we show in the paper where we present this serializable flows, it's slide 18, I think, that this can be achieved with acceptable performance. Now, well, maybe I guess I don't have much time to talk about this, but let me skip this. It's too much of detail for the moment, and summarize by saying that we achieve this very strong consistency property thanks to the declarative programming model that gives the runtime a lot of power. And the features of this declarative programming model that enable our serializable flows are explicit data dependencies, the topological order of evaluations, the write-once semantics that I mentioned, and the fact that application state is encapsulated in reactive abstractions. So due to explicit data dependencies, we are able to determine the reevaluation schedule of our flows ahead of executing them, which is the key for avoiding deadlocks and aborts. So explicit dependencies give us deadlock-free thread-safe propagation. The topological order of the evaluation enables this strong property even if the dependency graph changes dynamically. So we do support changes of the dependency graph on the fly, which is important for the open dynamic world that I mentioned in the beginning. The write-once semantics enable the execution of transactions of the flows in a pipelining mode, so values can be made visible to other flows instantly. They can be committed if you want when they are written, because there will be no other update of these values within the same flow. So it can be made visible to the other flows. And this is kind of the green meaning affordable. So the kind of orange color says semantically transparent. Due to deadlock-free propagation, we cannot observe any change in behavior, and the pipelining makes the execution efficient, while the fact that any application state is not directly cannot directly be manipulated from the outside, is encapsulated into reactive abstractions, enables to plug in thread safety transparently into applications. As I said, I can take the same program and run it single-threaded or multi-threaded without needing to change the program. And basically, we also show that this can generalize to distributed flows. Of course, there we need a little bit of distributed coordination, but this is minimized to transaction graph testing. I mean, these are details, but the fact is we have managed, even in distributed setting, to minimize the amount of coordination that we need, and then we have it's completely hidden from the application developer. It happens behind the scene. The runtime does it for it. But nevertheless, any distributed coordination, be it so little, has problems with availability, which we don't want to sacrifice. That's why we also support fault-tolerant flows. And for this, basically, I call it replicated data types 2.0. We basically bring these ideas of replicated data types from the centralized setting down to the local first computations, from the data storage, from the database down to the application. We give them to, we kind of develop them such that they can be given to the hands of application developers. What does that mean? This means that the REScala runtime has support for lattices, their properties, verifying the properties of lattices, combining lattices, composing them, and so on and so forth. So basically the programmer can, you don't need to read again the code, but given some data type, some custom data type, not data in a database, but some application level data type, in this case, the example is a counter, I can, as a programmer, say, okay, take this counter and turn it into a conflict-free replicated data type by providing a merge operator. And a nice feature is that I can also get several replicated data types, combine them into a more compound data type, like a social post, being composed of messages and likes and dislikes and comments. And then the runtime will derive automatically a lattice representation for the social post from lattice representations of its ingredients. Also important in a system where you don't have strong consistency, you would need to do some synchronization whenever connections are available. You need to disseminate changes across the distributed nodes, and there are protocols for doing so, and we have support for protocols for a range of different network topologies, client server, peer-to-peer, and especially also for delay tolerant networks. We are working on this at this point currently, but we see a lot of synergy between CRDTs and delay tolerant networks, which are very important for these scenarios of, let's say, agriculture 4.0 or environmental monitoring, where you don't have, you have only very unreliable connections, if at all. Okay, another thing that we need to add to replicated data types in the local first setting is support for encryption. In the centralized setting, I mean, you can assume that the different parties involved in a synchronization of replicas are trusted, but this is not the case. You cannot assume this in a local first setting where, as I said, parties can come and go, and where sometimes you can have problems with connectivity. I mean, when you cannot synchronize because there is a firewall or some devices are offline, and you might want to use kind of an intermediary. In this case, for example, Iris is kind of playing the role of intermediary between Bob, Alice, and Charlie if they cannot communicate directly with each other. But the problem here is that if you exchange the kind of the updates through Iris, then Iris might be curious to see the messages and violate privacy. So you want this synchronization to happen in an encrypted way. And here we also, again, this is ongoing work. We're adding an encryption layer, kind of having CRDTs that, in addition to the standard logic of being coordination, to enabling coordination through synchronization, also support encryption. And for this, we are adopting encryption schemes to make them synchronization free. With this, let's go back to our to REScala, so to say, to the application design in REScala. Now let's have a look at the same application, but supporting several decentralized devices collaborating with each other. And the program is the same as before. The only difference is that we have things like replicated lists. So we have these replicated data types that I just mentioned that are integrated into the language with support for encryption and so on and so forth. And then we kind of encapsulate them in reactive abstractions into signals so that they now also become capable of propagating their changes to their replicas in the distributed local first setting. Now this ends up with our dependency graph, so to say, with our distributed dependency graphs that are connected via potentially unreliable network connections. And at these points, these connections we use replicated conflict-free data types, which result then in conflict-free distributed flows, if you want. The reactive replicated data types act as any other reactive locally, so they propagate changes in the local part of the dependency graph, but in addition, they also propagate changes to their peers, to their replicas. And once changes come from replicas in a local setting, they also propagate this kind of change further into the graph. And this ensures what I call end-to-end real-time consistency. So changes are propagated across the whole data flow graph. And by this, we basically support eventual consistency, actually strong eventual consistency, as Shapiro calls it, because it's eventual consistency without synchronization end-to-end. So in the overall picture of a REScala application is such that the state is split or distributed across, let's say, devices, data centers. Some part of the application may run on stable connections, some parts on unstable connections. In the unstable connections, the state might diverge temporarily, but then it synchronizes automatically when connections are available. And I also mentioned that we support crash failure. So once a device crashes, the state is periodically stored. And here again, we use the features of the programming model to ensure that we minimize the amount of state that we need to store. And once the device is up and running again, we can recover. And again, we model recovering again via change propagation through the dependency graph, just as any other normal change. So what is important to take home from this part is that we kind of, thanks to these managed data flows, the properties, this eventual consistency property of CRDTs generalizes to application level strong eventual consistency without the need to do anything about this in the application code. It happens automatically thanks to the way we manage data flows consistently or in a serializable way locally. Because one change might affect several replicated data types, and in order to maintain causal consistency, you need to do this kind of automatically. Or you need to create new data types that kind of compose existing ones, losing modularity, which we don't need to do because our serializable flows ensure that the state of the entire application moves in a lattice, so to say, moves from bottom to the top of a lattice. The whole application state builds itself a CRDT, if you want. Okay, so now we have both. We have the possibility to have strong, consistent flows and eventually consistent flows within the same application in REScala, and we can use this feature to configure the application. So parts that run on stable connections can afford strong consistency, and parts that run on unstable or less stable connections, we can configure that part to use our fault-tolerant flows. Another ongoing work is that we are developing an approach to derive, I call it good enough consistency for safety properties. So the developer, again, is not responsible for configuring consistency levels directly, but expresses just application level safety properties that are important to be maintained during the whole execution. And then the language runtime, by analyzing the data flow of the application, which is very explicit, can verify with respect to the behavioral specifications with the safety properties and derive what we call synchronization points. Those are flows that need to be run strongly synchronized in order to maintain the safety properties. Okay, with this, I'd like to summarize the talk, which is about data-driven applications that nowadays very often are implemented in a centralized way. I explained that the centralized architecture is not a good fit for the new world in which we have this very powerful devices and data centers on the edge, if you want, which I use to motivate the need for supporting local first computations, for moving features that we have developed for the cloud, for the centralized setting down to the edge to enable new illusions for this decentralized world. And I then presented what we have been doing in the context of the REScala language with this respect in order to support this illusions of simplicity by basically language integrated support for managed consistent flows. And yeah, I basically emphasized how the language features, the declarative programming model enables the runtime of the language to offer very powerful features out of the box. Now, as I said, the picture going from kind of the centralized setting, moving all the benefits or the solutions we have developed for the centralized cloud setting down to a local first model of the world is a lot of work ahead. To mention some aspects, some threats we are exploring right now. I mentioned already that we are looking at synergies between replicated data types and delay tolerant network protocols. There are very nice features that would allow, for example, to design delay tolerant network protocols specifically for replicated data types and the other way around. We want to explore tierless programming or global programming, choreographic programming models for, tierless programming for automated cross-layer placement. So you want maybe to put some computations on the CPU of a device, but some of them directly on the chip, on the sensor chip. But also choreographic languages for collaborative computations on the edge. And there is great work happening in that space. And of course, when we talk about data-driven applications, AI doesn't, we need to, the talk should mention AI or learning-based systems. And I believe that this, the features of the REScala language or similar features are very well suited for peer-to-peer continual learning at the edge, but this is something to explore in the future. And as you see, there is a lot of more challenges ahead. But for now, for today, I would like to stop here to thank you for your attention and would be happy to take questions now, if there are any.
Thank you, Mira. And for everyone, I would invite you to just open your microphone and talk if you have questions, or write in the chat if you prefer, and then I can read the question for you. Meanwhile, I have a question while the others come out with theirs. A question related to the let's say, performance, if you want, associated to the execution of a program written in your language. I understand that clearly there is clearly an overhead that is intrinsic in the fact that there is a need for synchronization. What I was wondering is whether you had the chance to, for instance, compare the result that a normal programmer, an expert programmer would come out with in terms of overall program and their its performance compared to what to the outcome of your approach and how they look like.
I mean, we did compare for the serializable flows. That's exactly the comparison that we did. I mean, we did some micro benchmarking, but also we did a comparison. The same application developed with very fine-grained locks by a developer, by a specialized, an expert in the area on the one hand side, and on the other hand, the same application running on a optimistic transactional memory system. And basically, as you might expect, of course, there was some overhead compared to the handwritten, very fine-grained locking version. But this, of course, comes with the cost of having no idea about the correctness of that solution, even if you assume, and the assumption that the programmer is someone that knows what he's doing. But this was not an overhead, kind of unacceptable. And on the other hand, the performance was much better than transactional memory, using transactional memory system below. So that's why what I call the affordable in terms of performance. Because we minimize the synchronization, and again, key in minimizing the synchronization is the knowledge of the runtime about the explicit dependency graph of the application. And the same thing with fault-tolerant flows. For example, there we even worked on a version of REScala for the Wi-Fi chip. Reactify was called. I mean, it's a simplified version of the language, but again, the fact that the compiler knows the data dependencies gives the compiler a lot of power to optimize the computations. To group, for example, all computations that depends on the same values, to rearrange them without affecting the semantics.
Okay, thank you. And do the others have any question?
I would have one.
Please.
So currently this is all implemented in Scala. So I was wondering, like, why did you choose Scala over maybe other languages? And also, are there plans to bringing this, like, I think really great technology to other programming languages?
Yeah, good question. So why Scala? I mean, the decision for Scala was made a long time ago, not only for this particular project, but for all language projects in my team. So in former times, we were using Java, and it was impossible to explore new language ideas at some point in a Java setting, because every time you had to change the compiler. The good thing about Scala is that it was designed to support embedded domain-specific languages. So the syntax is very flexible to enable you to add domain-specific abstractions, or abstractions that are not in the language, like the reactives are not really domain-specific, they are general-purpose abstractions, into the language as by implementing libraries, basically, but nevertheless, these abstractions feel as if they were built into the language. So you don't see the difference, so to say. And nevertheless, the whole REScala is implemented as a library. So there is no change in the Scala compiler. Now, the other question is whether we have plans to move to other languages. Yes, I mentioned, for example, this is not REScala exactly. Reactify is kind of a version of the REScala's model, but very specific, is for C. So we compile to C in that setting. We are working on a version for Rust to replace that Reactify, because the idea there would be to, as I said, to have this multi-tier, multi-party formulation of the logic and then have the compiler split different parts on and put them on different devices. Either these old devices, these parts run on Rust in that case, but the overall idea would be to compile to different technologies because to cope with the heterogeneity of different devices. But we are not that yet. And Scala is a functional, it has a lot of support for functional programming. So REScala is basically is functional programming at its best. Reactive functional programming.
Hi, Mira. Thanks very much for a nice overview. One thing I don't quite understand is where this language is not particularly useful for, right? What applications would you not recommend people using this approach? Very lossy applications or very, time sensitive is not that interesting because in time machines will be fast enough to handle it. But is there, with a high level of transaction or a high level of updatability, I don't really understand where the boundary is of utility. It's a
challenging
question. Yeah. Yeah.
Because when you have a hammer, right, you think it's applicable to everything. But I wouldn't, I don't have a good answer to this. I don't think there is. It's general purpose. It takes a while. I think you have to get used with a new way of thinking about computation. So it's a paradigm shift, putting data flows in the center and not the control flow.
Right.
So basically, I positioned it in the area of data-driven applications. Now, there are applications that are not data-driven, like our batch processing, but even there, it doesn't mean that they cannot be redesigned to put data flows in the center. And I think, for example, REScala, we were thinking about this, is probably very suitable for microservices, to generate microservices from this declarative specification of the application logic, because all user computations are basically microservices, are functions that you can place wherever you want. So I don't think there are limitations. Now, we don't have we don't have experience with really, there is for a research language, I think it has a very stable implementation. It has been used by a lot of students to produce case studies, and for a research language prototype, it has it comes with quite some case studies, but it's a huge room to investigate the applicability or limitations in reality. But we make the experience that, in fact, this study that I mentioned was done with students, but there were two groups, one group working with Java and the other group working with REScala. And the Java group basically was taught Java and OO from first semester, while the REScala group had a tutorial of two weeks, two lectures, I think. And then they had to look at, program the same application in different ways, and also answer questions about, get the application and answer question about what it's doing, how a change will be implemented. And we were surprised ourselves to see that the REScala group performed much better than the Java group. But in the beginning, they complained that they kind of didn't really understand how to do this. But at the end, they did it faster and in a more correct way. So,
okay, and
it needs larger scale studies.
Okay, and for that example, did this actually run in a distributed environment, or did it run on an emulator?
No. So this was not on a distributed setting. It was not a distributed application. So the goal there was to see how well. So you would say when the class of applications is those where you need anything that is message passing, I think.
Right.
This is a much better way than using, I think message passing is way too low level. Why not let the compiler generate the messages that need to be exchanged between the parties. And these reactive data types are a great way to hide, let's say, the message passing complexities from the application developer. They work with data types, right? So that's something they know from the local setting.
Right.
And this is a very broad class of applications.
Yeah, that writing a debugger for this would seem to be a challenge, but.
No, not really. We have a debugger. You have to write a specialized debugger, but this one can be very powerful then because it has the data flow graph in its hand. So you can do back in time debugging, but you have to design a new debugger.
Yep.
Not
okay. Thank you.
Well, maybe I can move on with the questions. So it was very interesting. Thanks for this talk. I wonder, I missed something very fundamental. I missed it. I forgot. I didn't find it. So how do you deal with the situation that two independent agents, however you want to call it, actually change the same, update the same shared data structure, and you propagate this somehow? But how do you decide who wins at the end? The classical situation.
So this is hidden. I mean, you can have different strategies hidden into implementations of different replicated data types. So there are data types that encode this last writer's win, for example. They are called like this. So the way you synchronize changes is encoded into the implementation of the replicated data types. That's the key. The application developer does not need to care about this.
Yeah, but that means you care about it in that sense. That's my question. So how do you care?
Right. So we care in the sense, right. So in the sense that there are standard libraries, like you have libraries in the languages for concurrent data types, you have now libraries for replicated data types. And that's what I said. We do have a standard library plus support for turning a normal data type into a replicated data type. The programmer has to say how to merge state, right? This merge operation. Plus, what is important, composability. So given a set of replicated data type in your library, make it easy for the developer to compose those and have the runtime derive the merging semantics from the merge semantics of the individual components of the compound data type.
Okay.
I think there is, I mean, not only I think, I know. The good thing is there is a huge amount, I mean, there is great work on replicated data types out there that comes from this area of centralized clouds, geo-replicated clouds. And I keep seeing papers in, I mean, the database community conferences are full of those papers, but also the PL conferences like PLDI and even POPL, where people come up with even ever sophisticated ways to derive mergeable semantics from some high-level specifications of a data type. So get a sequential specification of the data type and pre and post conditions invariants that must hold. Then these approaches give you, for example, derive the merge semantics of the data type so that it's usable in a distributed setting.
So would it be correct to say that you do not provide any specific solution to this problem, but there are solutions, of course? So,
right.
I'm just curious.
Yeah, no, it's completely right. What we do, our contribution is in making this available to application developers, because those solutions are developed for databases, for geo-replicated databases. So there is a fixed amount of such data types into the database, and there is no way for you as application developer to add custom or application-specific data types to make them replicable. And that's where we add. So our contributions are in the sense of software technology contributions, not contributions in the synchronization logic.
Okay, thank you.
Okay, so I guess it's time to close this session, unless there are further questions. And let me thank Mira a lot. I think that we really appreciated the talk, and this will be made available. I mean, the recording will be made available, I think, in the next couple of days to all those who registered to this webinar. And then after, I think, 30 days, it will be posted on YouTube on the open channel that Informatics Europe has. So we will communicate, we will send you the link to this recording pretty soon, probably tomorrow or the day after. Okay, so thank you again, and hope to see you next time. Bye-bye.
Bye.
Bye.